I've talked a lot about how our change in internal energy of a system can be due to some heat being added to the system or some work being added to the system or being done to the system. And I'm going to write it again the other way, just because you see it both ways. You could say that the change in internal energy could be the heat added to the system minus the work done by the system. So there's two questions that might naturally spring up in your head. One is, how is heat added to or taken away from a system? And how is work done or done by or done to a system? The heat, I think, is fairly intuitive. If I have and we'll be more precise in the future of this, but I just want to give you the sense of what we're talking about. If I have some system here, some particles in some type of a canister, and it's at temperature, I don't know, let's say it's at temperature T1. I'll even give it a measure. Say it's at I don't know, it's at 300 Kelvin. 300 Kelvin. If I want to add heat to this system, what I can do is I can place another system right next to it, maybe. Right next to it. Who knows what size it is. And it's got some particles there. But its temperature is much, much, much higher. So its temperature is going to be, so this system's temperature, let's say T2 is equal to, and let's say it's 1,000 Kelvin. I'm just making up numbers. So what's going to happen in this situation? You're going to have heat transferred from this second system to the first system. So you're going to have heat going into the system. Now, heat and work and even internal energy, this goes back to our conversation of macrostates versus microstates. Heat is changing the macrostate of our systems. This system is going to lose temperature. This system is going to gain temperature. But we know what's happening on a micro level. These molecules are going to lose kinetic energy. These molecules are going to gain kinetic energy. How is that actually happening? Well, we assume that there's some type of a container here. Maybe it's a solid wall. These molecules are going to bump into that wall, are going to make the particles in that wall vibrate, and then they're going to make the particles in the green container's walls vibrate. And so when the green container's molecules touch the wall, they're going to bounce off with even more kinetic energy, with even more velocity, because of that vibration in the wall will push them back even further. So that's essentially how you get this transfer of kinetic energy, or this transfer of heat. But I think that's really intuitive. If we put this next to a cooler, a system with lower temperature, we would lose kinetic energy, or we would lose heat. And there's other ways that we can do it. We could compress the container. Well, I don't want to talk about that just now, because that'll be touching on work. So how can we add or subtract work to a system? And this one's a little bit more interesting. Let's go back to our piston example. Let's go back to let me just draw some lines here. So I have my container. There you go. It's got a little movable ceiling to it. That's my piston. And go back to the example, because what we're going to be dealing with, especially once I go into the pressure volume diagram, the PV diagram that I'm about to go into, we want to deal with quasi-static processes. Processes that are always close enough to equilibrium that we feel okay talking about macro states like pressure and volume. Remember that if we just did something crazy and the whole system is in flux, those macro states aren't defined anymore. So let's say we want to do a quasi-static process. So I'll have pebbles instead of one big rock. I'll draw the pebbles a little bigger this time. And I have some pressure. So that's my piston, and it's being kept down by these rocks. It's being kept up by the pressure of the gas. The gas is bumping into this ceiling. It's bumping into everything. The pressure at every point in the container is the same. It's at equilibrium. Now, what happens in that example where I removed one rock from that? So let me copy and paste that. So if I remove one rock from this thing right here, you copy and paste. So that's the same thing. Now let me remove a rock. I'll remove this top one was removed. What's going to happen? Well, I now have less weight pushing down on the piston, and I have a certain amount of pressure pushing up. The system, it'll very temporarily go out of equilibrium, but we did a very small difference in how much we're pressing down on it. So hopefully it won't be a huge change in our equilibrium. We'll stay pretty close to it. But we know from the previous example, instead of this thing flying up, it's just going to shift up a little bit. And this is just going to shift up a little bit. Right when we do it, it's going to be like that right there. And let me fill in that part with black because it's not like the space disappeared. So let me fill that in right there. So our little piston will move up a very small amount. And what I claim is when this happened, when I removed this little pebble from here, the system did some work. And let's just think about that. So work, according to the definitions that you learned in first year physics, and when you just do using classical or dealing with classical mechanics, you learn that work is equal to force times distance. So if I'm claiming that when this piston moved up a little bit, when I removed that pebble, I'm claiming that this system here did some work. So I'm claiming that it applied a force to this piston, and it applied that force to the piston for some distance. So let's figure out what that is, and if we can somehow relate it to other macro properties that we know reasonably well. Well, we know the pressure and the volume, right? We know the pressure that's being exerted on the piston, at least at this point in time. And what's pressure? Pressure is equal to force per area. Force per area. Right? So the area, remember this piston, there's some, you're just seeing it from the side, but it's a kind of a flat plate or a flat ceiling on top of this thing. And now what distance did it move it? Let's just call that, I could blow it up a little bit. Let me, it moved it some, I didn't draw it too big here, some x, some distance x. Right? So this change, it moved it up some distance x there. Right? So what is the force that it pushed it up? Well, the force, we know it's pressure. The pressure is force per area. So if we want to know the force, we have to multiply pressure times area. If we multiply both sides of this times area, we get force. So we're essentially saying the area of this little ceiling to this container right there. It could be, I could draw it with some depth, but I think you know what I'm talking about. It has some area. It's probably the same area as the base of the container. Right? So we could say that the force being applied by our system, let me do it in a new color. The force is equal to our pressure of the system, pressure, times the area of the ceiling, times the area of the ceiling of our container, of the piston. Now that's the force. Now what's the distance? The distance is this x over here. The distance is, I'll do it in blue. It's this change right here. I didn't draw it too big, but that's that x. Now let's see if we can relate this somehow. Let me draw it a little bit bigger. So, and I'll try to draw it in 3 dimensions. So let me draw the piston. What color did I do it in? I did it in that brown color. So our piston looks something, I'll draw it as a ellipse. The piston looks like that. And it got pushed up. So it got pushed up some distance x. Let me see how good I can know. Whoops, let me copy and paste that same. So the piston gets pushed up some distance x. Let me draw that. It got pushed up some distance x. And we're claiming that this is the force. Sorry, let me be clear. This is the force, and this is the distance. Right? So work is equal to our force, which is our pressure times our area. Pressure times our area times the distance. Right? I wanted to be very clear with that because when I wrote this, I said, okay, the force that we're applying is the pressure we're applying times the area of our cylinder. This is the area of our cylinder right here. That's the area of our cylinder right there. So if you do the pressure times this area, you get the force. And then we moved it some distance x. Right? Now, we could rearrange this. We could say that the work is equal to our pressure times our area times x. What's this? What's this area right here, times x? Well, that's going to be our change in volume, right? We've increased this area times some height is some volume. And that's essentially how much our container has changed in volume. When we push this piston up, the volume of our container has increased. You can see that even looking from the side. Our rectangle got a little bit taller. But when you look at it with a little bit of depth, you see the rectangle also didn't get taller. We have some surface area. Surface area times height is volume. So this right here, this term right here, is a change in volume. So we can write work now in terms of things that we know. We can write work done by our system, work done, is equal to pressure times our change in volume, times change in volume. Now this has a very interesting repercussion here. So we could, we can rewrite our internal energy formulas. So for example, we can write internal change in internal energy is now equal to heat added to the system plus the work, let me say minus the work done by the system. Minus the work done by the system. Well, what is the work done by the system? Well, it's the pressure of the system times how much the system expanded. Right? In this case, the system is pushing these marbles or these pieces of sand up. It's doing work. If we were doing the other way, if we were adding the sand and we were pushing down on our little canister, we would be doing work to the system. So this is the situation where I'm doing here, where I'm removing the sand and the piston goes up. Essentially, the gas is pushing up on the piston. The system is doing the work. So if we go back to our little formula, that internal energy is heat minus the work done by system, so done by, then we could write this as this is equal to the heat added to the system, heat added, minus this quantity, the pressure of the system, times the change in volume. It is interesting. If the volume is increasing, then the system is doing work. And this applies, we're going to talk a lot more about engines in the future, but that's how engines do work. They have a little explosion that goes on inside of a cylinder that pushes up on the piston, and then that piston moves a bunch of other stuff that eventually turns wheels. So when the volume increases, you're actually doing work. So I'm going to leave you there in this video. In the next video, we're going to relate this new way of writing our internal energy our formula, and we're going to relate it to the PV diagram.